Like I don't have a big book. Like just undertaking. Yeah, that's nice. What lens are you using? Jax. What lens? It's not here today. Like I don't really know what. I think I'm just gonna do all my notes and you got canceled. I was gonna call.
Bad mood. Let's postpone.
It got rescheduled.
Oh man.
Tomorrow.
It's been a rough day, put it that way.
Yeah, so you want I bet you got up super excited, like, yeah, baseball. Ridley. Do you like eat yeast?
Started out good. I got free coffee while I was
Were you on Thursday? Is it free coffee there?
No.
We might.
No, I just walked out. I had to wait in line. Like, I didn't have to wait in line. The machine wasn't working right. So I had to wait for them to fix it. She's like, you know, just walk out with it. So it started out a good day. Yeah.
Was that the peak of the day?
It's a shame. That was the peak of the day.
Yeah.
Yes, at like 6:45 in the morning.
Yeah.
6:30, probably closer to that.
You know what the peak at like 9 a.m. is like for my days? Then it's like all this.
9 a.m. every day.
9 a.m. is when and from that in the day just gets tired.
Interesting. So you had like that. What about like daylight savings? Did it go to 10 or 8? Like, did it ever switch?
No, it's straight 9 a.m.
Always 9 a.m. What if you like are in California? So 6 a.m. or still 9 a.m.?
No, it's 9 a.m.
9
It's
a.m.
always 9 a.m. Pacific time.
Whatever local time is, 9 a.m.
That's what it is.
That's
Because I'm not like one of those kids who like freak, like it's just like, oh, waking up is a chore. Like I wake up fine. I can get right nice and early, get a good breakfast.
all right. Fair enough.
Take a shower, brush the teeth.
So Jordan, to answer your question, Miss Taylor is not here today.
So we got ready.
No, so I'm officially going to be your sub today.
Can I go to the library?
And tomorrow and Wednesday and from here on out. She decided after Friday, too much work, a lot of stress, whatever you want to call it, teaching, and that's the whole reason they do student teaching is to decide is that the profession they want to get into. So she is done. She said to say goodbye to you guys. So I don't know what else to say. Like I said, they kept getting worse.
Were you
I got the
surprised?
texts a little bit surprised. Are you?
Yeah, I'm surprised.
I mean, it just happened so quick.
Say it again.
It just like happened so quick.
It was very abrupt. Yeah. She said it wasn't you specifically, Samson.
Okay.
So
I thought it was me.
that's a good thing. She did say calc. She just didn't specifically say set 8 or 6. Yeah.
Those hooligans in Set 6.
I'm not saying it again for Mason. Not for his benefit.
Yes.
So back to the same old, same old. That was way too easy. April Fool's, a little early, right? But yeah, she'll be back tomorrow. She has some personal stuff to take care of today. That was so easy though. Like, you guys bought hook, line, and sinker. Completely bought that.
I didn't buy it.
You weren't here to buy it. You were late.
That was a good performance.
That was pretty good, wasn't it?
That was really
She goes into accent.
Yeah.
No one knows.
All right.
It was too stressful that she was done teaching. She wasn't going to be there anymore.
Jordan, are you crying?
really good.
All right. But anyway, we do need to move on here. We are going to continue through. I am subbing today for you guys. You've done definite and indefinite integrals at this point, and so far, think about derivatives. We've had many types of derivatives, right? We started with the power rule, and then what other kind of derivatives did we have after power rule? Quotient rule? Product rule? Chain rule. And then your trig derivatives. So we've done power rule for integration and trig integration so far. Today we're going to get into essentially what is the product, quotient, and chain rule of integration. It's all lumped into one thing, which is a nice part. Okay, so as far as integration goes, there's power rule, there's trig integration, and then there's what we're going to talk about today. In order to get to that today, we have a little bit of background stuff to work on. And the first thing we're going to talk about, we're going to refresh on the fundamental theorem of calculus. That is your definite integral. So the fundamental theorem of calculus, or FTC for short, is simply the integral from a to b, again, you guys saw this already, of f of x dx is equal to the integral of f evaluated at b minus the integral of f evaluated at a. So that was your fundamental theorem of calculus, your definite integral. You guys just had a quiz on that along with indefinite integrals. There is a second fundamental theorem of calculus, which you guys are going to basically try to generalize based on a couple examples we're going to do here. The second fundamental theorem of calculus deals with derivatives and integrals as well. It's going to make a random quadratic function that is a function of t. We're going to integrate it from a constant, 1, up to a variable x. So we're going to apply the fundamental theorem of calculus in order to hopefully derive a pattern that will allow us to define the second fundamental theorem of calculus. So forget the integral symbol right here. How do I derive this? What's the integral of t squared plus t plus 5? Good. Okay, so you do things as normal. We're evaluating this from x to 1. And then ultimately, just to keep it equal, we are going to derive all of that. Well, how do I evaluate this going from x to 1? What does the fundamental theorem of calculus tell us to do? Yeah, plug in x and plug in 1. So I have the derivative, 1/3 x cubed plus 1/2 x squared plus 5x, right? That's f of b, minus, and I'm going to get a little lazy here, and I'm going to do minus a bunch of numbers. Why am I allowed to be a little lazy there? Why do I not care what numbers are in there?
Because they'll just be like I mean, when you, I don't know how to run this, but like when you do the,
Starts with a D, yeah.
Yeah, the derivative, they won't be there anymore.
Correct. Remember what we're doing to this. We're taking the derivative of this. If this number is 20 or 12 or -5, what's going to be the derivative of it? 0. So I don't care what these numbers are because when I go back and derive them, they're going to turn into 0 anyway. Now what happens when I take the derivative of at least this f of b portion? What do I get? Not 2/3 x squared. You guys are forgetting how to take derivatives after integrating for so long. X squared, good. Right? 3 times 1/3 is 1. X to the, drop the power by 1. X squared. Plus x plus, and then technically minus 0. Okay? Don't need to write minus 0, right? What do you notice about this result right here? You got it. It's the same thing as that right there. It's our original function with what slight exception?
The x is at t.
Yeah, we substituted the x in. Notice we're taking the derivative with respect to x of an integral that was with respect to t. Okay, so we just did a basic substitution. We'll look at one more example of this and see if we can generalize it then. We'll take the derivative of the integral going from -2 to x of cosine t dt. What do you think the answer is going to be? Cosine of x. Good. Okay, so what's the integral of cosine? Sine. So the derivative of sine of x evaluated from x to -2. Whoops, sine of t, I'm sorry. Sine of t going from x to -2. So in other words, the derivative of sine of x minus sine of -2. What's the derivative of sine? Cosine. And what's the derivative of sine of -2? 0. So did we get the result you expected? Yeah, totally did. And again, that is exactly what we started with one exception, the t became an x. So if I want to go back to this page here and generalize the second fundamental theorem of calculus, we can say the integral, well, the derivative of the integral going from a to x of f of t dt. By the way, where a is a what? A constant, right? It's going from a number up to some variable of f of t dt is equal to what? F of x. You got it. That is the second fundamental theorem of calculus. Right there. Now you have to pay attention to, and if they do this, they're trying to trick you, which you're not going to see a whole lot. Notice this derivative is with respect to x, and this gets evaluated at x. This derivative, this integral is with respect to t. So all letters need to match up, right? You can't integrate something with an x and a dt, t and dt, or it could be a z and dz, a v and a dv, as long as those letters match up, just like with derivatives. Okay, there's no implicit integration. You have to have the same letters lining up there. All right, so that is the second fundamental theorem of calculus. One last example for that before we move on to our product and chain rule and stuff. Think about this one before you jump to a conclusion. We're going to go from 1 to x cubed. Not to x, but to x cubed. We'll stick to a trig one. We'll do sine of x. Sine of t, sorry, sine of t dt. What do you think the answer is going to be? Sine of x cubed? That's probably what most of you are thinking, right? Anybody have anything different they're thinking?
Sine of 3x.
Sine of 3x. All right, we combine the two, then we're getting closer. Let's see how this plays out and see if you guys can figure out why. So we're going to integrate first. What's the integral of sine? Not cosine, but negative cosine. Good. We're going from x cubed to 1. So I'm going to take the derivative of negative cosine x cubed minus negative cosine of 1. What happens when I take that derivative? Forget about the negative, but what happens when I take the derivative of cosine of x cubed? Chain rule. So the derivative of negative cosine is positive sine of x cubed, but what do I need to multiply by? Not x cubed, 3x squared. And then of course we have the minus 0 for this part. So our final answer is 3x squared sine x cubed. How can I generalize something like this when it's not an x, but it's an x cubed or an x squared or an x to the fourth? It wasn't just I'm going to plug in x cubed, but I also need to do what? Take the derivative of it. You got it. So if we want to throw another generalization in there, the derivative of the integral going from a constant to, and we'll say x to the nth power of f of t dt will equal what?
X to the n minus 1.
Yeah. That function evaluated x to the n still, but then don't forget to take the derivative of that. Okay, chain rule process there. That is the derivative of x to the n. So the same as the original second fundamental theorem of calculus, but the chain rule's involved there. Okay? In reality, second fundamental theorem of calculus isn't used that often. Okay? Even the examples in our book, there's no real-world examples of them. It's just like, hey, do the second fundamental theorem of calculus. That means you don't need to integrate, you don't need to derive. You just replace the letter. But don't get slipped up and forget to do the chain rule when it applies. If you think about it, when it was just going from a constant to x, what's the derivative of x? 1. So we were still doing chain rule there, but when you multiply by 1, do you actually write times 1? No. Okay, so you always need to take that derivative. Remember, the chain rule has always been there. A lot of times it's times 1, you just don't notice it. Okay? So make sure when it is there, when it's noticeable, you make sure it ends up there. Okay? So let's do one example then without actually integrating and deriving. We'll take the derivative going from a to 4x cubed of cosecant. Now let's make it the square root of cosecant x minus 1. I keep doing the x's. Cosecant t minus 1 dt. We don't even know what the integral of the square root of cosecant t minus 1 is. But because we know the second fundamental theorem of calculus, we know our answer is going to be what? 12x squared, right? We took the derivative of this piece times? Not quite. Cosecant x minus 1. Yes, sir.
It says f of x to the n. Shouldn't it be x to the third?
Oh, absolutely. Absolutely. Thank you.
Like, was it so it's 4x to the third? Or is
Yep, yep. And that's where the derivative of 4x cubed is a 12x squared. There's our chain rule there. Yep, thank you. Yep, you plug in wherever it's going to and from. Okay? So that's the second fundamental theorem of calculus. Again, not a major part of the course, not a major part of calculus even, because you could integrate and derive just as simply. All right, however, this next one is a major part. Chain rule, product, and quotient. And I'm going to put them in quotes because this is not called the chain rule of integration, or the product rule of integration, or the quotient rule of integration. It has its own name, and it's called U substitution, or simply U sub for short. If you guys got that on the quiz on Friday, or I guess it would have been Thursday for you guys, you had to skip on Friday. That's something that you would have been able to do, but what would your first step have been? Multiply it out. Right? You would actually have to do x cubed plus 5 times x cubed plus 5 times x cubed plus 5 times x cubed plus 5. And then times x squared. So it would be a really annoying integral to take. But that's what you would have done. Now with U substitution, we can make that process a little easier. This looks like a product rule right here, right? X squared times. And it also looks like a chain rule because there's x cubed plus 5 inside of to the 4th power. So if it has the appearance of a product rule, a quotient rule, or a chain rule for derivatives, then you're going to use U substitution in order to integrate. And I'm going to let U equal x cubed plus 5. And you'll see why, and hopefully you'll start picking up on patterns of what U is going to be. I'm now going to take the derivative with respect to x. So what's the derivative of U with respect to x?
3x.
No, not the derivative of x cubed plus 5. The derivative of U.
Du.
Du dx, you got it. And now, Jordan, let's go to the other side.
Okay.
What's the derivative of x cubed plus 5?
3x squared.
3x squared. So du is the same as 3x squared dx. Everybody agree? Remember what du dx or dy dx or any of that stuff means. That's your slope, change in y over change in x. So this portion right here is just the change in x, and this is the change in u, your vertical component. All right, rise over run. So you can separate them. You're making it into what's called a partial derivative now. Well, if I look at this, right, how big is that? Right there. What color are we in? Yellow? 3x squared dx, and I decide to do this. Have I changed the value of my integral yet? That's just a weirder looking version of the same thing, right? 3 times 1/3 is 1. I just wrote a fancy form of 1. But notice what I have now. Oh, crap, wrong color. Yellow. 3x squared dx. So I have 1/3 integral. What replaces x cubed plus 5? U. To the 4th. What replaces 3x squared dx? Du. Can you guys integrate that?
Yeah.
Pretty easily, right? What's the integral of u to the 4th? Yep. 1/5 u to the 5th. And don't forget the plus c, good. So my final answer is 1/15 x cubed plus 5 to the 5th plus c. Andrew, how do I check if my integral is correct?
You can just derive it again. And then,
Let's derive it again then.
Oh,
5 times 1/15?
that should be 1/3.
1/3 x cubed plus 5 to the 4th.
Oh,
Don't forget chain rule. Times
wait a minute.
times the derivative of x cubed plus 5
3x squared.
times 3x squared. So I have 1/3 times 3. What's that become? 1. So I end up with x squared, x cubed plus 5 to the 4th. Okay, gets us right back to the original thing. If you couldn't visualize that, go ahead and actually do it on your paper. Okay, that is the integral of x squared times x cubed plus 5 to the 4th. If you were doing this prior to learning U substitution, you guys would still be raising that to the 4th power right now. Right? You'd still be multiplying that out. And it'd be very, very tedious. And then you'd have to try to factor it. Okay, so U substitution simplifies that process a lot. Comes in all kinds of forms. Let's look at some examples right here. And I have a sheet here for you guys to write this stuff down on. Jordan, I thought you were going to cry. I really did.
You got me good there.
So you guys are not allowed to tell set 6, by the way. I'm going to do the same thing with them. I noticed you guys probably already see you already got your phone out. Now you're like taking your tweet off. Miss Taylor did not stop. Come
You're a good actor.
Thanks, Jordan. Maybe you're just bad at hiding it. All right, so number 1. What do you think, knowing that the goal is to take the derivative of u, what do you think I should choose to be my value for u instead of multiplying out and distributing all this stuff?
X squared plus 1.
X squared plus 1. Because you know the derivative will be what?
2x.
You got it. Whoops, I wrote the derivative instead of the x squared plus 1. So du dx will be 2x, which means du will be 2x dx. So this will turn into the integral. What replaces x squared plus 1? U. So I have u to the 4th. And what replaces 2x dx? Du. Are there any questions on that substitution? Right, this is all multiplication. So you could think of this as x squared plus 1 to the 4th and then times 2x dx. Right? Order doesn't matter. They don't have to be next to each other. Right? It's multiplication. So 2x with a gap and then dx is the same as 2x dx. Okay, so this is a straight substitution right here. 2x dx. Notice everything is in terms of u right now. We need those letters to match up. And this is an easy integral now. It's 1/5 u to the 5th plus c. And then, of course, our final answer, we plug u back in. Plus c. The one to the right of this. You cannot integrate any other way besides u substitution. Right? I can't distribute that out. There's nothing to do. You can't send 3x squared into a square root function. What's my u value?
Square root of x cubed plus 1.
Okay, I heard two different things. I heard the square root of x cubed plus 1, and I heard x cubed plus 1.
X cubed plus 1.
Why x cubed plus 1?
Because it's to the half power.
X cubed plus 1 is not to the half power. I said why x cubed plus 1. You said because it's to the half power.
Well, because like, just from looking at the one before, like if you're to take u, it's like the thing in parentheses, so like you can change
You
u
don't want.
Looking for a simpler answer than all that other stuff.
Derive the square root.
No, it's still easy to derive in the square root.
Definitely.
What's the key after we take the derivative?
Put back in.
Yeah, you have to be able to plug it back in. What's the derivative of a cubic? Any cubic.
Quadratic.
Quadratic. Do I have a quadratic that I can use to replace it? Yeah. Okay? So the key is that when I derive it, that's in my original function somewhere. If I try to derive a square root, I'm going to get a 1 over something. I have a reciprocal function at that point. I don't have any reciprocal functions in here. So du, and if you feel comfortable enough, you can skip a step and jump right to this. Right, instead of writing du dx and then multiplying by dx. Okay, if you don't feel comfortable, then do this step again. So now I have equals the integral. Instead of 3x squared dx, I have a du. And instead of the square root of x cubed plus 1, I have square root of u, which I'm going to write as u to the 1/2. Okay, and again, if you want to write out square root of u and then write u to the 1/2 after that, by all means, go for it. And what is the integral of u to the 1/2? Okay, so 2/3. U to the 3/2 plus c, good. So 2/3 x cubed plus 1 to the 3/2 plus c. Put that up there for those who need to see it. Trig derivatives. Excitement. Which one am I choosing? What's my u? Tan x plus 3. By the way, every opportunity you have, add that constant in there, right? The plus 3. Because what's the derivative of a constant? 0. Okay? So it makes it nice and easy. So u is tan x plus 3. By the way, I'm impressed with maturity. I only heard one person mumble the typo here.
I see it.
I was up there my first year I did this, and the whole class like went nuts, and I just haven't changed it since. Kind of makes a nice little break in the action. Andrew just saw. Andrew just oh. Good, you got math on your mind, Andrew. Good for you. Tangent of x plus 3. What's our derivative? I think we lost Jordan for the whole period now. Secant squared x. And I'm moving that dx over right away. We good with that? Okay, everybody sees that step I'm skipping there? What's my new integral now? I'm done doing the replacements for you. You tell me what the new integral is. Just u du? Yeah. Secant squared x dx is a du. Tangent x plus 3 is a u. And make sure, I know I said it's multiplication, it doesn't have them next to each other or stuff, or anything like that, but the integral sign starts integration, and the du, the dx, the d whatever ends integration. Okay, that's what helps you avoid needing parentheses for integrals. So make sure that du, or whatever letter it is always the last thing. It ends what you're integrating. All right? So what is the integral of u with respect to u? You got it. 1/2 u squared plus c. And I'm sure some of you are at the point where you can skip that step and just write 1/2 tangent x plus 3 squared plus c. Lots of areas to skip steps and save space. But again, feel free to write everything out so you get comfortable with that. This fourth one, kind of like our first example, is going to have a little hitch in it. We have a quadratic and a linear. Which one's going to be my u? The quadratic, absolutely. So what is du equal to? Okay, here's a little hiccup. I don't have a 2x. So how do I have a linear function, I just don't have 2 times x. I have 1 times x. Yeah, no, go ahead, Norm.
The 1/2 on the outside and 2.
You got it. So I'm going to rewrite it completely because I have trouble squeezing it in here. if I rewrite that integral as 1/2, and then a 2, and then x times x squared plus 1 to the 4th dx. Does everybody agree that's the same as the original? It just looks a little weirder? It's like writing, if you remember from trig, sometimes you wrote pi as 3 pi over 3 so you could find your reference angle. It's still pi. It's just a fancier form of pi. Okay, same idea here. So what do I get when I do my u substitution, actually substitute my u value in here? What's my full integral that I need to integrate? Well, I heard Alex say the 1/2. Jaden, I did not hear you say the 1/2.
That's not outside of it.
Correct. But it can also be on the inside too. Remember, you can pull constants out. They can also go inside. It's part of our integral. So it's 1/2 u to the 4th. The 2x dx became the du. What's my final answer? Not next step. Who's got our final answer if we jump to it? Jordan?
1/10 times x squared plus 1 to the 5th. Let's see.
You got it. Right on. All right, you guys can wrap up the last two there. Notice they're very similar to the first, well, the second and third ones. Okay, but they have coefficients involved there. So see if you can figure them out on your own. Yes, your question?
Oh, yeah, that's equal. We keep it equal now.
From the line before. All right, this line and then equals, I'm writing a new line. Right, remember math is trying to work down, not across? So you always put an equal sign, so it equals the previous thing coming through. Yeah, it's not like a left and a right side or anything. Yeah.
So do you have this
Boys are
on the outside?
You got it? A 1/3 and a 3? Now again, that's something that you can skip. Or you can just do 1/3 and then know that what's getting substituted with the dm.
Okay.
But just be careful that if you do that and mess it up, it's hard to get partial credit then.
Okay.
But that's the whole looking a step ahead type thing. You guys good over here? How way up front here?
I think I did something wrong.
Doesn't make any sense. It would be 3x squared.
Wow, it'd be 3x squared.
du and
Oh, wait.
You okay, you guys under
3x
control?
squared dx. Bill. You just do that.
You guys good down here? So would you guys have called it if I didn't spell it?
Then we take
That's a while ago.
You missed the plus sign. It's going to be 2 plus 3 derivative of tangent squared. The plus c. Correct. Yep.
most certainly was the thing. Makes sense. Then you do the, then we get all these things that you did to But you keep it du, so it's like du.
As you guys finish those two, I got one more example for you, then we're done. Yeah. You you can, or you can just pull the two out. Which the 1/2 and the 2 on the inside would have canceled out. You would have the 2 on the outside anyway.
You guys will not forget it.
Now go for it.
Where's that?
I don't like this week.
Got a vote? I know where you
Choose
go.
the X equals Y to actually have.
So you want to have 3 x, you're gonna get 1/3. XQ plus 1 by times 3x squared, cancel out 1/3, so you get x squared. E to the 1/2.
Yep.
Really? Really?
You guys get the second one yet?
Am I on the right path in this situation?
So you chose U to be x cubed plus 1, so you got 3x squared.
This is right.
Yeah, but what do you need to do to that x?
2 nuts.
Because you don't have a 3x squared.
What do I do like once I'm here?
Yeah.
Well, remember the du has to end the integral. It can't be in the middle there. So you integrate that. So you get 2/3. Yeah. And don't forget plus c. And don't forget to add 1 to the exponent. You left it the same. And that would be 2/9, right?
What did I do wrong?
Yeah.
So you need to, before you do, you can't do U substitution yet because not everything gets substituted. You need to change x to 3x squared and multiply by 1/3 out here. Because 1/3 of 3 is a fancy form of 1, right? Just like we did up here with the 1/2 and the 2.
That's what I said actually. You did something wrong.
So 1/3 3x squared, U 1/2.
Well, write everything in terms of x until you write everything in terms of u. Right? Never mix letters. Keep it all x's, and then when you have all the pieces to substitute, don't get your dx yet. See, now you have all the pieces. 3x squared dx gets replaced by du, and square root of x cubed plus 1 gets replaced by square root of u. No, there's no square sign there though. Yeah.
So I go.
So you have 1/3, next line is 1/3, integral, square root of u, or u to the 1/2, either way, du. Because 3x squared dx is du,
That's the.
and
that
x cubed plus
replaces
1,
that.
yeah.
Okay. Sounds good.
Special.
So what did I do wrong?
Where did the u squared over 2 come from? Where'd you, okay, so where'd you square root disappear from? That's what you did there. So you integrated u, but you didn't substitute fully, correct? You got a 3 and you want to know when it actually say u to 1/2.
They got, well, no, for the grade here, they got.
Well, the derivative of x cubed plus 1 is not x squared.
So you're multiplying central by 1/3.
Yeah.
6 foot to 6, 2 foot to 8.
You get this,
Oh,
Alright.
There you
Oh,
go.
you pulled the 1.
What happened?
dx.
I'm not showing all my stuff.
Now do all your substitutions here.
And
He was here for
All right, guys, I'm going to start working these out on the board, so if you need to follow along to check, go for it.
You move back to Cleveland. So you go forward, but yeah, it's like you couldn't have equals 1.
No, I did that earlier. Do that again.
Yes. Oh, yeah. This is a cable guy.
You originally only had the x
Yeah.
squared, then you needed a 3x squared. I just multiplied by 3.
Actually, I might go with like a fat head. Really? How bad was your freaking loss?
So there is the bottom left one.
Actually,
Bless you. And And there is the last one.
You take out the two and out one.
So are you guys looking at this one right here?
Yeah.
So I could have done 1/2 and 2 if I wanted to, but I just factored out
Okay.
the coefficient there. Okay? It would have been the same thing if you did a 1/2 on the inside, because 1/2 and 2 would have made a 1 anyway.
Mm-hmm.
So remember, you can always take constants out as needed. Right? And then you get that result. Any questions on either of those two? Okay, rather than do the last example, which is definite integrals, I'll let Ms. Taylor start with that fresh tomorrow. The definite integrals and U substitution. But you do have a small homework assignment tonight dealing with second fundamental theorem of calculus and U substitution. I'll jot that down here. So second fundamental theorem of calculus, and you have 10 minutes to do these. I'd knock these guys out at least right away. Page 293. 75 to 92, and just pick random problems from throughout there. Don't do them all. Okay, make sure you do some where it's going from a constant to x, and some where it's going from a constant to like x cubed. Okay, do a variety of them. There's 3 different sections of problems in there, and then U sub is on page 304, and those same deal. Pick a variety of problems from 7 to 34. Now, be careful, and I'm guilty of doing this as well, because textbooks kind of get you in that mode of doing that. Not everything in that 7 to 34 section requires U substitution. Okay? So don't get stuck thinking like, crap, I'm trying to do U, and I'm taking the derivative, nothing's there to replace it. Sometimes you can just take the integral as is. Okay, so don't think every single one of those 28 problems is going to be a U substitution problem. Okay, they mix them and match them, so you need to recognize when to use it and when not to. Just like with derivatives, you need to know, is this a product, quotient, chain, or power rule? Okay, so you do need to recognize when to use which ones. All right, again, you have 10 minutes. Jordan, the phone should be away and the textbook should be out.